Hey everybody, welcome back to chemistry, and we are continuing on our tour of looking at various different kinds of molecules to see what kind of structures they have. In other words, where do the atoms on the molecules position themselves in space? So now we're going into more complicated molecules, and the molecules I'm going to be talking about now all have a central atom with 5 electron groups. So let's go ahead and get started. So the first kind of molecule I want to talk about is a molecule that is called AB5. And I'm just going to hold it up just for a second here. And what I'm kind of hoping you can sort of see is that we have a central atom here, which we're going to call A, and it's bonded to 5 atoms. So these atoms are B, and so we can call this molecule AB5. So this is an AB5 molecule. Now, it is part of the large family that includes a variety of molecules that have 5 electron groups. So let's talk about why that's the case. So again, when you're sort of thinking about electron groups, you focus in on the central atom, and then you ask yourself this question: does the central atom have any lone pairs, or does it have any bonding groups? And here in this structure here that I have, the central atom doesn't have any lone pairs. However, you can see that there are 5 single bonds emanating from the central atom, and so it has 5 bonding groups. So the total number of electron groups that a central atom have is just the lone pairs plus the bonding groups. There's 0 lone pairs, there are 5 bonding groups. So the total electron groups around the central atom is 5. So we have 5 electron groups from the central atom. Okay, so now let's just take a look at one particular molecule that has this structure. So the example here is phosphorus pentachloride. And so let me quickly write out its Lewis structure. So we have phosphorus in the center. And so this is going to be a molecule where the phosphorus atom has a number of electrons that's greater than an octet. And what you can sort of see is that the phosphorus atom has 10 electrons, 10 valence electrons on it. And so that's perfectly fine. And the reason is phosphorus, as I recall, is in period 3. And if you have elements in period 3 or 4 or 5, they can have more than an octet of valence electrons. They can have 10 or 12 usually. And so here we have an example where phosphorus has 10. Okay, so this is sort of a nice Lewis structure of the molecule that I drew, but it doesn't really kind of tell us much about the actual shape of the molecule. And so let's look at the model here to sort of understand the shape of the molecule. So there's some important details of the shape that you need to know. So first off, again, notice that I have a central atom here in purple, and I have 5 atoms that are bonded to it in green. I want you to know where those atoms are in space. And so one thing that you might be able to see is that we really have 2 kinds of atoms here of the 5. So one kind you can sort of see is where you have 2 atoms on the opposite sides of one another. This top atom here, this bottom atom here. They're on opposite sides of one another. These are called axial atoms. Now, what I'm going to do is I'm going to turn this on its side like this. And so now what you can sort of see is that now the axial atoms are sort of pointing into the screen. But look now what we can clearly see, the other 3 atoms. They're in a triangle, and they're in the same plane. And so they're in a triangle, and they're in the same plane, and they're sort of equatorial to these axial atoms. And so we call these 3 atoms in a triangle in the same plane equatorial atoms. So you need to know that those, in this AB5 molecule, you can have those 2 types of atoms. So let me sort of draw a 3-dimensional picture of this as best as I can. So we have phosphorus in the center here. And so we have 1 chlorine atom, which is axial. And then we have another chlorine atom, which is axial. And then what I'm going to do is, the best of my ability, is draw 3 additional chlorine atoms which are equatorial to these axial chlorines. So we have 1 chlorine here. I'm going to put an E here for equatorial. And then we have a chlorine heading out maybe toward me. So I'm going to use a wedge here that's filled in. And then we have a chlorine going into the glass board, so it's CLE like that. So one thing I want to do is sort of remind myself here that these three chlorine atoms here, the equatorial chlorine atoms, they're all on the same plane. So I'm going to draw sort of a triangular shape here, which I'm hoping will remind myself that these atoms are in the same plane. Now, another detail you need to be aware of this molecule. So again, I'm sort of holding up the molecule here, and I have the axial atoms going up and down. One thing I want you to notice is the angles between these atoms. So first, let's look at an angle between the axial atom and the equatorial atom. And I think you can sort of see that's 90 degrees, right? But then let's flip it on its side. And I think what you can see now is that the angles between the equatorial atoms are 120 degrees. So this makes sort of an important point, is that in these molecules that have 5 electron groups, we actually have 2 different angles that can be between the atoms. We have 90-degree angles, and we also have 120-degree angles. And so this is sort of the first time we've seen this complexity. And so I want to indicate that in my drawing here. So going from here, say, the axial atom to the equatorial atom, this is a 90-degree angle. And going from these equatorial atoms is 120 degrees. And so that's a detail which you have to sort of be aware of. Okay, so let's look at, again, going back to the central atom and seeing how many lone pairs it has. And so you can see that here in this molecule that we have AB5, it has no lone pairs. So there's 0 lone pairs here. And so also you can see each single bond here going to one of these 5 atoms counts as a bonding group. So there are 5 bonding groups. And so remember how you evaluate total electron groups that the central atom has. You add up lone pairs plus bonding groups, and that gives you the total electron groups. Okay, so now you have to figure out the name of the so-called electron geometry around the central atom. So the way we do that is, here's the central atom, and so again, we're thinking of all the electron groups around the central atom and how they arrange themselves in space and what kind of shape that basically takes on. And so here it's a little bit simple in that we don't have any lone pairs, so the electron groups are just the bonding groups. They're the 5 bonds. So what I'm kind of hoping you see is that here you can sort of think of this axial atom as the tip of one pyramid. And so I'm going to rotate this. And so you can sort of see the base of the pyramid here are the equatorial atoms. And so we have the tip of one pyramid, but then there's the tip of a lower pyramid. And so there is the base of the pyramid here, which is the equatorial atoms. So we really have 2 pyramids here in this structure. And the base is a triangle. So this geometry is called trigonal bipyramidal, because there are 2 pyramids. Okay, and so what you'll see here, again, we don't have any lone pairs. We have single bonds to atoms. And so the shape that these atoms assume in space is the same as the electron group geometry. So the molecular geometry is also trigonal bipyramidal. And so that is something you'll need to know. Okay, so now let's continue on to another family of molecules here. And so this is what I call the AB5, caught it, AB4E family of molecules. So this is the AB4E family of molecules. And so this actually also has 5 electron groups. So let's see why. So I have an example here of an AB4E molecule. And so what you can sort of see here is that it looks the same as an AB5 molecule, but we've replaced one of the atoms with a lone pair. So it was AB5, now it's AB4E. The E, again, the lone pair replacing one of the atoms. Okay, so what's an example of this molecule? So a great example of this molecule is sulfur tetrafluoride. So let's draw the Lewis structure for that. It looks like this. Okay, so you can see sulfur is bound by single bonds to 4 fluorine atoms. So that's fine so far. But then sulfur has a lone pair. So even in the Lewis structure, you should be able to see that the central sulfur atom has 5 electron groups, 1 lone pair, and then 4 bonding groups, which are the 4 single bonds. So a total of 5 electron groups. Okay, so let's try to figure out what the structure of that molecule is in space. I think an easy way to sort of understand where you would see the lone pair in this molecule is just to kind of point out that one of these atoms here, of the 5, 2 of which are axial and 3 are equatorial, one of them is going to be replaced by a lone pair. So the question is which one? Will it be an axial atom or will it be an equatorial atom? And the answer is you're going to remove an equatorial atom like this to create a lone pair. So you might ask, well, why did you do it with the equatorial atom and not the axial atom, and is there a difference? And the answer is yes, there is a difference between removing an atom and putting in a lone pair in the axial position versus the equatorial position. So let me explain that for a second. So let's say we put a lone pair here in this axial position. So lone pairs are pretty bulky, right? And so what they're going to do is this lone pair will have 90-degree angles with these 3 atoms. But imagine here you put a lone pair here on this equatorial position. And so what I'm going to do is I'm going to rotate this a little bit so maybe a little bit easier to see. So you're imagining here you're putting the lone pair here instead in this equatorial position. Here, in the equatorial position, we still have 90-degree angles between these axial atoms, but we don't have 3 atoms at 90 degrees. We only have 2. The others are at 120 degrees. And so what I'm kind of hoping you can sort of see is if you put this bulky lone pair in the equatorial position, it has a little bit more space than, say, if you put it here in the axial position. It'll have less space because there are 3 atoms at 90 degrees. So it goes into the equatorial position, and that's something you need to know. So when you draw a structure of this molecule, so we have sulfur here in this case, and we have an axial fluorine like this, which is not removed because it's axial, an axial fluorine here. And so what we have to do is replace one of the atoms with a lone pair, and it'll be an equatorial atom. It'll be that one, for example. And then what we have here are the other fluorines, one heading out toward me and one going into the board here. And so again, what you can sort of see is that these 3 atoms here, or I should say 2 atoms with the lone pair, they're all in the same plane. But the angles are pretty much almost the same as before. They're going to change a little bit because we have a bulky lone pair here. That's going to tend to press these 2 fluorines in this direction together. So the angles will be from the lone pair to the fluorine will be a little bit greater than 90 degrees. But in general, this 90-degree angle, this angle is about 90 degrees, and the angle between the equatorial atoms and lone pairs is about 120 degrees. Okay, so let's look and analyze the central atom. We have a central atom has 1 lone pair. You can see that there. Bonding groups. It looks like the central atom sulfur has 4 single bonds to fluorine, so there are 4 bonding groups for a total of 5 electron groups. Okay, so now we have to get some names for the electron geometry and for the molecular geometry. So let's figure that out. So here is the AB4E molecule. And so what is the electron geometry of the central atom? So again, the electron geometry is just the lone pairs plus any of the bonding groups which are single bonds. We have 1 lone pair and we have 4 single bonds, and they get as far away from each other as they possibly can in space. And so basically the electron geometry really hasn't changed any here from the AB5 molecule. It's exactly the same. So the electron geometry is trigonal bipyramidal as before. However, when we do the molecular geometry, what we do is we ignore the lone pair. So let me cover this up. And so we have a molecule here. So what does it look like? Well, imagine flipping this guy over like this, and I'm going to get a larger sample of this molecule. So here it is. Here's another AB4E molecule. You can see that it has a lone pair. I'm going to flip it over on its side. What does it look like? E. It looks like a seesaw. Ha ha. Okay, so here are the anchors of the seesaw. It's going back and forth. My 10-cent possibility for humor there. And so this is a seesaw molecular geometry. All right, let's continue on. So the next molecule is an AB3E2, and it has 5 electron groups. So let's take a look at it and see why. So here is an AB3E2 molecule. So I removed here another atom with the previous molecule, put it in a lone pair. And so now you can see we have a central atom connected to 3 peripheral atoms, which are 3B atoms, and then 2 lone pairs. And so I'm hoping you can sort of see, it's a little bit difficult to see, I need a larger model here, but this thing has 5 electron groups, 2 lone pairs, and 3 single bonds emanating from the central atom. So the example of this molecule here is BRF3. So let's draw a structure of that. So what does that look like? So its Lewis structure is bromine. Here is one fluorine. Here is another fluorine. Here is another fluorine. They have lone pairs like this. Okay, and then the bromine has 2 lone pairs. So you can see that the bromine, the central atom, is breaking the octet rule. So it has 10 electrons. Okay, so let's do a 3-dimensional picture of this. It's the same as before, but what we're going to do is take off another one of these equatorial atoms and replace it with a lone pair. So it looks like this. We have bromine in the center. And so we haven't touched the axial atoms. So they're still there. In this case, the axial atoms are fluorine in this molecule. We have one of the lone pairs, and then we have a second lone pair here that's equatorial to this one, and then we have a remaining fluorine that's part of the equatorial system here. And so again, these 2 lone pairs and this fluorine are in the same plane. I'm not going to draw that out. Okay, so in this molecule, let's look at the central atom. There are 2 lone pairs. And so bonding groups, these are the number of single or multiple bonds leaving the central atom. And so we see we have 3 fluorines with each with a single bond. So there are 3 bonding groups leaving the central atom. So how many total electron groups around the central atom? It's 2 lone pairs plus 3 bonding groups, so it's 5. And so this continues to be a trigonal bipyramidal electron geometry. So I'll write trig bipyr. And then what is the molecular geometry? Well, here is the molecule. So you can see that there are 3 atoms here with 2 lone pairs, and you can basically see it's shaped like a T. So this is a T-shaped molecule. Okay. Now, the last family of molecules for here, the ones here which have 5 electron groups, is an AB2E3 molecule. It will have 5 electron groups, as you'll see in a minute. So let's just write out the Lewis structure of the example. So this is xenon difluoride. And let me just digress a second. So here we have an interesting situation where you see a noble gas actually bound to another element. So we have a noble gas in a compound. And so remember we were talking about noble gases really not being able to react with other elements because they tend not to want to give up electrons to other elements, nor do they want to accept electrons from other elements. Under certain conditions, you can get the noble gas xenon to give up some electrons to fluorine atoms and bind with them. And so you can create several different kinds of xenon fluorine compounds, and one of them is xenon difluoride. This was figured out about in the 1960s. Anyway, the guy who figured it out should have gotten the Nobel Prize, and he did not, unfortunately. So let's draw a Lewis structure. It looks like this. We have a xenon bound to a fluorine, bound to another fluorine, and so it has 3 lone pairs, looks like that. So you can see there are 5 electron groups around the xenon. Okay, structure. So we continue on plucking off atoms from the equatorial positions to create lone pairs. So you pull that off, and this is what you are left with. So let's draw this. So we have xenon here in the center. One fluorine is axial, the other fluorine is axial. And so all the equatorial positions here are assumed by lone pairs like this. And so just remember that these lone pairs in these equatorial positions, they're all in the same plane. Okay, lone pairs that the central atom has, you should see there are 3 there. Bonding groups, again, bonding groups are single or multiple bonds. We have 2 single bonds, so there are 2 bonding groups. There are a total of 5 electron groups. You can even see that in either structure, right? As electron groups are just the lone pair numbers added to the bonding group numbers. Electron geometry is still trig bipyramidal. And so here is another sort of structure of this molecule. Again, what you can see is the equatorial positions have lone pairs, and then the axial atoms are there. And you can see just looking at the atoms, ignoring the lone pairs, all the atoms are in a line. So one fluorine binds to xenon on the opposite side of the other fluorine. They're all in the line. Therefore, this is a linear molecule. Linear. All right. Thank you for listening to that. We will see you next time.